All right. I think I got all of it under control. There is a little bit of a cross breeze, so there might be a little shimmering noise in the background. I'm sorry about that. All right. So we finished we finished last time with chapter 4. There's one little section that I want to cover from chapter 4, and that's chi-square. And once we're done with this, we're gonna be on to chapter 5. Um, chi-square won't show up till chapter 6, and that's in a week or so, week and a half. So I have to finish writing that chapter, and then when I have that, I will upload the PDF for that, and then we can talk more about it. So chi-square is a cool little feature which we're going to be introducing now, and then short break and hypothesis testing, which, if you have been paying attention to chapter 3 and 4, should be a breeze, for lack of a better term. So let's get down to chi-square. I suppose we should. So for all intents and purposes, a chi-square distribution looks like this. It has a starting point at 0, 0, and goes up and then goes down and out to infinity. This symbol is chi. So chi-square is this right. All right. If you wonder how to draw it, it's a X which has one straight side, one flamboyant. So this is chi-square. Notably, something is knocking. Hang on. Notably, chi-square distribution is not symmetrical. Well, we could say duh, it starts at one point and goes to infinity, so it has this one of those shapes. But this aspect of or the lack of symmetry as an aspect plays an important role, which we're going to hopefully get into it soon. Part 2 is that values are non-negative. And this is important, and again we're going to get to why. We use degrees of freedom we used to define them in last aspect as df. Degrees of freedom, as degrees of freedom go up, it becomes more symmetrical. So the more degrees of freedom we have, the more this shape shifts over away from this anchoring point and starts getting more and more symmetrical. All right, and here's the last little bit. Before, when we looked at a z-score, the critical values refer to the area from the left up to the critical value. And every time we did that, when we're looking at a z-table or a t-table, we were starting at negative infinity and going up to the z-square, and that was the area covered by the critical value, or the critical value referred to that area. In case of chi-square, the critical values give our, our a border for the area to the right. Right, so all the area up to the critical value is what we're looking at. All right, so this is the very basic. This wind is. Maybe I should. So this is this. All right, so how do we find the critical values? So let's look at an example. Imagine we have a sample of, say, 9 and a confidence level of 95%. We want to find the critical values. Well, we don't know any better, so first things first, let's draw the sucker. Alright, so now confidence level of 95. You don't know how to do it. I'm assuming you haven't looked it up anywhere, you're just kind of befuzzled by it, just as I am. So what can we do? We could approach it the way we've been approaching confidence levels before. 0.95 is in the middle. Right? This is 1 minus alpha. If this is 1 minus alpha, how big is alpha? Well, alpha is 0.05, it's 5%. Well, if 95 is in the middle, let's say we have some area right here and some area right here. This one is alpha over 2, and this one right here is alpha over 2. There are 2 at 2.5%. Okay. So we know that the critical values are responsible for the area to the right, which means that this critical value, whatever it is responsible for all this area, and this critical value is responsible for all this area. How big is this area? Well, this area is 0.025. How big is this area? Well, this area is 2.5% plus 95%, so it's 0.975. So far, everybody's with me, hopefully. So now, let's look at our tables. And if you pull up your chi-square table, what we're looking for is, let's see if we can play this zoom in game. And now if we look at your table, chi squared, and there's a number underneath it. That's something. this refers to how big this area is. So how big our areas are? Well, we have 2.5% and 97.5 at n equal to 9. We don't have n, we have df. So we have to do one more little calculation here, and we have to say, hey, df, degrees of freedom, equals n minus 1. So in our case, the degrees of freedom equal to 9 minus 1, which is 8. Alright, so we're looking for degrees of freedom of 8, which is this line right here. And we're looking at 2.5%, which is right here, and 97.5, which is right here. So we're looking at 2.180. So the chi square here is 2.180, and the chi square for this was what? 17.535. Right. So again, smaller number on the left, since they are all non-negative. Larger number on the right. This is responsible for the 2.5%. This is responsible for the 97.5%. Alright, so we have a chi square here, chi square here. Before that, we had negative z alpha over 2 and positive z alpha over, negative t alpha over 2 and positive t alpha over 2. In this case, we have all positive. So how do we deal with this? I propose we add a little subscript saying right chi square, left chi square. It's not here, it's not on the table, but it makes sense. This way we know which chi square we are talking about. Alright, so this is how we find critical values. Questions? Double checking. Anybody talking to me? Nope. I swear it suggests I'm crazy. I talk to myself. Right. So this is done. So what can we do with this? Because doing it for our health is not exactly why most of you are here. Well, the reason why we're looking for it, one of the reasons, maybe differently. A chapter 4 reason to look for it is to build a confidence interval. Well, confidence interval of what? Well, of population variance. What's the symbol for population variance? Cannon squared. So how do we do it? Well, we know that, or we know, and you're going to find out, that chi square has this following formulation. Where n is the sample size, s is sample, S squared is sample variance, and sigma squared is population variance. If we move it around, multiply by population variance divided by chi-squared, what we can get is that. This moves here, this moves back. But we're talking about an interval, and we have 2 chi-squares, so logically I could do this on this side as well. And there's your confidence interval. Now, this and this looks exactly the same, but we know that we have 2 different chi-squares. So question is, which chi-square goes where? Well, let's think about it. If you have 2 fractions, 1 over 2 and 1 over 17, which fraction is bigger? 1 over 2 or 1 over 17? Because the top is the same for both sides. We took some sample, and this sample has some variance. So both tops are the same. The only difference is the bottom. Right? So whatever the top is, the bottom is the one that makes the fraction bigger or smaller. Which one of them is bigger? 1 over 2 is bigger than 1 over 17. Half is better than 1/17. Alright, so if 1 over 2 is bigger, then this should be bigger. That's left, that's right. And there's your confidence interval for population variance. Alright, well, can we do more with it? Well, we could build a confidence interval for population standard deviation. Well, what's the symbol for standard deviation? Sigma. How do you get from sigma squared to sigma? Well, you take a square root, right? Since standard deviation cannot be negative, there's no issue in taking a square root of a square. Well, if you take a square root of this, we should probably take a square root of both sides. By the way, this square is not a square we're going to be dealing with it. We're going to be dealing with chi-squared. And so if you want to take a square root of chi-square, you just don't remove the square, right? Because the value in the table is given for chi-squared as a variable. All right. And on this side we have n minus 1 s squared chi. And there's your confidence interval for population standard deviation. Easy enough, I suppose. Right. Degrees of freedom times a square of sample standard deviation or sample variance divided by a critical value, which we know how to get. So let's do one problem just so we are fresh on it and moving on. So imagine we have a sample of apples. And so we look at the sample size, say 12, I'll make it 13 apples for luck. And we know that the standard deviation for the sample is 0.2. Construct a 90% confidence interval for population variance and standard deviation. Alright, well, where do we start? Well, we should probably start with critical values. And there's your chi-square. 90% is in the middle. So if 1 minus alpha is 90, alpha comes out to be 0.1, which means alpha over 2 is 0.05. And alpha over 2 equals to 0.05. And we have some chi-square left here, and we have some chi-square right here. And so how do we find them? Well, first things first, we have n, but we need degrees of freedom. And degrees of freedom equal to n minus 1, so degrees of freedom equal to 12. Alright, so now we're going to look at our trustworthy table. And what am I looking up? Look, I'm going to look up this one first. So I'm looking at 0.05, and 0.05 is right here. And I'm looking at degrees of freedom of 12, which is right here. 0.05. And I'm looking at 21,026. And then I'm looking all the way up to here, so I'm looking at 95. And if I look at chi-square for 95%, and we're looking at degrees of freedom of 12, we're getting 5.226. Alright, so that was done, and then we're going to construct a confidence interval for the variance. What is it? N minus 1, that's 12, times S squared. Well, this is sample standard deviation. So if our S equals to 0.2, then our S squared equals to 0.04. So the S squared, which is 0.04, divided by left one, which is this 5.226, and on the other side we have 12, 0.04 divided by 21,026. Again, why? Because the formula that we're using is that one. So let's plug those numbers in. So 0.04 times 12 divided by 21.026. Zero point zero two two eight smaller than sigma squared smaller than 0.04 times 12 divided by 5.226. And we're done. We don't know where the population variance really is, but we are 90% sure it's somewhere between this and that. Alright, so how do we find standard deviation? Well, standard deviation symbol is just sigma, as we remember from here, which means I just have to take a square root of 1 and the other one. And there's my answer. So part 1, part 2. And so this is how you solve these problems. Again, because we're doing square roots and because we might be dealing with small numbers, it's paramount you keep extra decimal places lying around, just in case. I used 4 and 3. Now, if the answer expects me to get 2, well then it's easy to fix. Right? But more decimal places is better, because when it comes to square roots, if you make the decimal place too simple and too short, there's a good chance your scores are going to be off. Now again, if they're a little off from my answer key, that's fine. But if there's a big difference, that will affect your results. Do I see any questions? No, and according to this, I'm the only one watching myself. Well, that's sad. Alright, this concludes chapter 4. So this was chi-square and chapter 4. And I'm going to take a 2-minute breather. My throat is closing up. and then we continue with chapter 5. All right. I hope everybody's back, or at least possibly back. All right. So what's next? Let's do chapter 5. Let's do hypothesis testing. By the way, this is how much we covered so far. All this. Time flies when we're having fun. Right, so chapter 5, hypothesis testing. Hypothesis testing. Hypothesis testing is testing whether or not a claim is valid. Now, I try to be careful and not say true, although we're going to use the word true in the future, because we are not talking absolute truths. If you want an absolute truth, you need to run the census, and if you're running the census, that defeats the idea of just taking a sample. So, what we're going to do is we're going to take a look at a statement, collect some sample, and then we're going to see how the sample matches up with the statement. All markers in this cup are black. Well, let's take a sample. Is it true that all markers in here are black? No. But to the best knowledge we have, right, it suggests that the markers in this cup are black because this is what we had. Right, so the question of absolute truths is a tricky one, to say the least. So we're going to be testing if things are valid or not. How do we do it? Well, first things first, we ought to build a set of numbers we can deal with. So claims, for example, like this. Most vegans are happy. That's a big statement, right? You post it on a blog, there's going to be a meat eater that's going to hate you for it. That's a big statement. It's a statement about the population. Right? How do we quantify it in a way we can deal with? Well, first of all, we can quantify most. What does it mean, most? Most means more than 50%. No, what's most? Well, proportion, right? Either you're happy or unhappy. And there's your claim, right? Average grade in a stats class is 72%. Okay, well, is 72%. Well, 0.72. And what's on this side? Is it a P? Well, we have percentages, so we would want to say P, but here's the important word. It's an average. Either this way or this way, depending on what we are dealing with. If we are saying percentages, this. If we are using percentages just as a unit, then this. But both of those give you some statement about the population. Alright, so how do we go from there to the next piece? Well, we need to remember the rare event rule. We talked a little bit about it. So the rare event rule says the following. If the probability of an assumption occurring is very small. If the probability of an assumption occurring is very small, then the assumption is probably wrong, incorrect, false. I like incorrect the best, but that's up to you to decide. If the probability of an assumption occurring is very small, then the assumption is probably wrong. Hang on, I'm gonna move my mic a little bit. Getting some weird feedback here. Hopefully this will help with the feedback. I think the wind is getting into the mic. Alright. What's important about it? The important word about it is here. What does mean probably? Well, how about reasonably or confidently? Right? So this tells us that we'll be doing some statistics that we've been doing. And then question is, what is very small? Well, very small is how significant you want to be, right? How much bias you're willing to ignore or allow into it. So that's the basic. So we all seen those really big full page ads talking about how this drug and that drug is going to do miracles to you. So what's a good drug? So a drug Let's say this. A drug company put out an ad saying that at least 80% of their patients were clear of AIDS after just one dose. You take a pill, AIDS goes away. Right? This is a statement we can deal with. So how do we deal with this statement? Well, let's take a sample of 100 people. Right? We're gonna infect all of them with or clear of AIDS, HIV. Let's make it a big thing. So we take 100 people, we take a syringe with infected blood and we stab all of them. And then we give them the pill. And we take a look what happened. How do we know this works? What's the status quo we would expect, if we take 100 people and stab them with an infected needle? I don't know what the infection rate is. I'm assuming it's about 10% of people won't get it. So if we do not use the drug, or any drug for that matter, we're expecting 90% infection. Right? If we don't use the drug, we're expecting 90%. So, being skeptical as we are, let's assume drug doesn't work. Let's make this very basic assumption, right? So we take 100 people, we stab them with the needles, and the drug doesn't work. If it doesn't work, right, we should, out of 100 people, we should get 90 infections. So here's my question. Let's say I do it once. I take 100 people, I stab them with the infected needle. I give a couple months for the HIV and AIDS to reproduce, and we're gonna take a look. What happens if I get only 88 infected? Right? Is my statement that the drug doesn't work true? Is the drug working because instead of 90 we got 88, right? This conversation begins of how different is this number from what we assumed would be, right? Is this good enough? We know that there should be 90% infected. We got 88. Is this big enough? How about if we get only 20 infections? What then? Right? The conversation we're trying to build is we have this concept of what will happen. In our case, the concept says, hey, 90% of people stabbed with infected needles are going to get infected. And then somebody comes in and be like, hey, we can clear up 80% of this 90, we can clear it up with one dose. Okay, you assume it doesn't work. You give people the drug, And the question is 88 different enough from what we were expecting to say, hey, that drug works. We got 88 infections rather than 90. Or is it too close? Right? Could it be that out of a random sample of 100 people, there were more healthy people and in good shape, right? Or our technicians made some error and we didn't get the infection rate we were expecting. Again, this is some average getting. Is this different enough? I wouldn't think so. Right? This doesn't prove the drug doesn't work. Doesn't disprove it. It's not different enough from here. On the other hand, if we take 100 people, we stab all of them, infected needles, and we only get 20 infections. Is it different from the expected 90? Well, yes. Can this be just a random fluke of, luckily we just got 20 infections? Sure, but what are the chances? Right? What are the chances that when we are expecting 90% infections, we only get 20? What are the chances? The chances are extremely small. And if the chances of that are extremely small, this assumption is probably wrong. Right? This is one of those things. Now, AIDS and HIV and stabbing people with infected needles, cruel and unusual. But we have drugs that are preventative. There is some, I think it's one of those is Truvada that prevents HIV infections. There's some anti-malaria drugs. There's some anti-fungi drugs, right? There's other drugs that have this similar aspect, and this is how we test it, right? Of course, in the laboratory, we do it on mice and monkeys rather than on people, but this concept is there. Right? How do you test vaccines against Ebola? Ebola, high mortality rate. So how do you prevent infections? Well, you make an assumption it doesn't work, and then you check. And if you get results very different, so this is kind of this basic idea. Is my sample, and again, this is the sample, which means that as far as you can tell, this is as real as it gets. Right? There was some assumption, which we assumed was true, and then we tested. And then you run your sample and you say, hey, is my sample different enough from what the population assumption I made to say something about that assumption? Again, based on this, what are the chances this is going to happen? In my opinion, extremely small. So when we talk about hypothesis testing, there's some aspects of it that we need to formalize. So first thing is we're going to talk about the null hypothesis. And the null hypothesis is a statement that the population parameter for this class, we're going to be talking about means and proportions, is equal to some value. And the equal part is important. So null hypothesis says something about the population. The population is this, population is that. Well, the notation for it is h sub 0. This is an h with a subscript 0 to it. says, hey, the mean is 20, or the population proportion is 50%. So null hypothesis has the symbol H sub 0. The opposite of that is the alternative. And in our case, the symbol we're going to be using for that is H sub 1. Now, some text and some sources will use H sub A, but the reason why I prefer H sub 1, because otherwise it's ho-hos and ha-has, and Christmas is far away. So the other one is alternative hypothesis. And what is alternative hypothesis? Alternative hypothesis states that the parameter, in our case mu or p, has a value different than the null hypothesis. What does mean different? Well, it could be that the value is smaller or greater, and lastly not equal. So there's some choices in that respect. So for example, the alternative hypothesis could be that the mean is greater than 7, or the alternative hypothesis could be that the proportion doesn't equal to 0.2. So that's the basics. Now what do we do with all this information? We have to look up the steps, at least conceptualize the steps. We're going to start by taking whatever the claim is, we're going to start with whatever the claim is, and we're going to try to sort it out into this. And once we have our null hypothesis, and I'm going to show you how to do it in a second, we're going to start by assuming that the null hypothesis H sub 0 is true. That's the first step. I mean, think about this the way you would argue with your drunk roommate. Your roommate comes around completely smashed and they are making big, obnoxious statements. Do you argue with them? If your friends are like mine, arguing doesn't get you anywhere. So you don't argue. You say, yes, Johnny, you're completely right. Yes, you're the smartest person ever. Yes, very good. Now go to sleep. So you assume it's true. Whatever the null hypothesis is saying, it is true. But trust and check, right? So then we're going to use the evidence. And what evidence we have? Well, we have some kind of sample. We're going to use the evidence to reach a conclusion. Now, what are the conclusions? Well, we could just right? Your drunk roommate comes in and be like, hey, I just met the richest person on the planet. okay, you know, I agree with you. You're completely drunk, so I'm gonna assume whatever you say is true. And then I'm gonna verify. Show me the selfie. Right? And if the person pulls out their phone and starts showing you selfies of somebody who's really rich, now are we going to argue about couple $1 billion here, couple $1 billion? Yeah, you met one of the richest people on the planet. Great. Or, they pull up a phone and show you a picture of the downstairs neighbor, and you're like, no, that's not really the richest person on the planet, right? So we have to look at it. It's very easy to say a statement. It's very easy. It's easier to show that what you have is rejectable rather than not. I just saw a super rich person. It's one of those big, cool statements. You can assume it's true. Now they show you a picture. It's relatively easy for most of us to say, hey, this is a super rich person or this isn't a super rich person. Now, we can argue where the line for super rich is, but most of us have a pretty good feeling of where it is. So your downstairs neighbor from your 2-story walk-up doesn't really count as a super rich person, which means that if you have that as an evidence, you reject it. Well, how do we reject it? I have enough evidence, right? My sample is big enough to prove or to show H sub 0 is wrong or incorrect. I have enough evidence. I can prove your statement wrong. What else can you do? Well, you could fail at this. Right? I met one of the richest people on the planet. You showed me a picture. It looks like the person is loaded. Can you say that they're the richest person? They're obviously very rich. So it's like, I don't have enough evidence to prove H sub 0 wrong. Right? You either see that this is obviously bogus or you're on the fence. Right? Now again, being on the fence doesn't mean you accept the statement. Just because you didn't disprove it or you show that it's wrong doesn't mean you accept, right? Because here's the juicy bit. You cannot accept the null hypothesis. And this is extremely important. Now, what else can we do to talk about? Court of law, right? If you get pulled into a courtroom, right, as the accused, what happens? Right? We assume you're innocent. Actually, write it out. Let's look at a criminal court. Step 1, assume innocence. Bam. Step 1. Step 2 is, right, check some evidence. And then what do we have? We have guilty and not guilty. Guilty means we reject h sub 0. That was our h sub 0, right? And here is we fail to reject. And as we've been hearing a lot, some people are shown to be not guilty, but that doesn't mean that they're innocent. It's just we don't have enough evidence to prove that they're guilty. Right? The difference between this and this usually is more evidence. But there is no way you can go from here to proving innocence. Right? We just kind of assume that if you're not guilty, you're innocent. But that's back to this assumption. The step is assume h sub 0 is true. You're innocent. Run evidence and then check. Are we rejecting this assumption or are we failing to reject that assumption? Right? Because innocence is so hard to prove, because everybody is guilty of something, we assume it's true and then we deal with this. Same concept. This brings us to interesting aspect. If alternative hypothesis is the opposition, so right, if the alternative hypothesis is the opposite of the null hypothesis, and we can only reject the null hypothesis, right? Then if you want to support a claim, and what do you mean by support? Well, it means prove it right. You must state it as h sub 1, not h sub 0. If you state your claim as h sub 0 with the language we would expect from h sub 0, you can only reject it. But if you state it as h sub 1, which is the opposite, right? Guilty means we're rejecting h sub 0, which means h sub 1 is true. Alright, I'm gonna let this hang, and while we do that, let's continue. So how do I identify which one is h sub 1 and which one is h sub 0? Well, first thing, we're gonna state the claim, the original claim. We're going to state it symbolically. We did that at the beginning of today, right? Vegans are happy and stat classes average as well. So we need to state this original claim symbolically. Then we need to state the opposite. We need to state the opposite. So those are the two. And here comes the big part. h sub 0 is the statement out of those two with the equality in it. Question, which one does it have the equal sign? So how do we do that? Let's say we have this statement. The mean of fluid is at least 12 ounces in a can. So what's the claim? Well, we have the mean, so mean, and at least is that, right? Greater or equal. So what's the opposite? Well, the opposite is mean is smaller than 12. So which one of those two statements has equality? Well, the top one. So from the top one, we know that this becomes h sub 0. Now, this is a new thing, or relatively new thing in statistics, is where we take whatever symbol is here and we just make it equal. So if it's greater, equal, or less equal, we just turn it into equal. Why? Is because 12 is the borderline between where we are okay and where we have a problem. If you get if you order a can of Coke and the can has 13 ounces of Coke in it, you're not going to be upset about it. But if the can of Coke that's supposed to have 12 ounces, it has 10, you're going to be upset about it, right? So if the teller in a supermarket gives you only 10 eggs for your dozen, you're going to be upset about it. If they give you a 13, you're going to be okay. So the border line is 12. So we don't care if you get more, as long as you get 12. But lower is the problem, right? So the null hypothesis becomes this, and the alternative hypothesis becomes this. Right? And again, the null hypothesis could be both the opposite or the claim, depending on where the equal sign is. This equal part is important, and that dictates where h sub 0 is. Alright, so that's very basic. So let's try a couple problems. What did we say here? Most vegans are happy. Well, the claim is P is greater than 0.5. The opposite of it is P smaller or equal to 0.5. Right? Most means more than 50%. So let's take a look at equal sign is here. So that becomes h sub 0, P equal to 0.5. And that becomes h sub 1. What else we can do? Average dozen of eggs has 12 eggs. Well, the claim is what? Well, that the average is 12. And what's the opposite? Well, the opposite says mean doesn't equal to 12. This becomes h sub 0, mean equals to 12, and this becomes h sub 1, mean doesn't equal to 12. Easy stuff. About 25% of people that don't practice will have problems with this when it comes to exam questions, because building the right claim and then turning into the hypothesis is a big part of how to solve those problems. So getting this right and getting this right is important. So how do we go about making the decision? Well, what we need to talk about is significance level. And we know the symbol for that is alpha. Again, the most common ones are 10, 5, and 1%. What significance tells you, it tells you how willing you are to make a mistake, to not see a pattern where there is a pattern and whatnot. So I'm willing to get it wrong alpha number of ways, but we're going to get to it. This alpha allows us to get a critical value. And what a critical value in this case is, it separates rejection it separates the rejection region from the fail to reject region. Well, I suppose we should say rejection region. What is that? Well, rejection region is the following. If we have a test statistic, so if our test statistic falls into this region, we reject h sub 0. Alright, I know this is a little dry, so let's expand it a little bit. So let's think about this example. Let's say we have a significance level of 5% and we have a null hypothesis, say p equal to 0.5. What are the options? Well, we could have an alternative hypothesis of p being smaller than 0.5. We could have an alternative hypothesis of p being greater than 0.5. And we could have an alternative hypothesis of p just not being equal to 0.5. Those are the three basic options. What does this mean? Well, it means that if we are to look at a standard normal curve. In this setup, we are okay with 50% or more. So we're okay with everything up to this part. Are we okay with just a little bit lower than 50%? Think about it this way. If you're expecting to get at least a 50 on an exam, or on an exam, how upset would you be if you got a 52? I think you'll be okay, right? What happens if you got a 49? Would you be upset? It's a hard exam. You're expecting to get 50% out of it. So 49 doesn't exactly, ruin your life. How about 48? 48? Still okay? Sure. How about 47? Well, it's 3% off from what I expected, but again, it's not that off. How about 15? If you get 15% from an exam that you're expecting to get at least 50 on, well, that's upsetting, right? So somewhere down here, there's a little area where you say, hey, this is completely different from what I expected, right? I assumed I'm going to get 50% or more. And suddenly I'm getting to this little area where the scores are just way too low. Now, how big is this area? Well, this area that you're upset about is that 5%, right? By the way, for those of you who have a hard time visualizing this way, just look at h sub 1 and think about it in terms of an arrow, right? That's a quick way to look at it. So anyways, this little area becomes 5%. What's the critical value here? Well, the critical value here was z alpha, not z alpha over 2, because we are looking at the whole alpha region. And if you look up 5% on your z-score, what you're going to get here is you're going to get negative 1.645. And that is like your critical value. On the other hand, if your alternative hypothesis was bigger than 50%, right? Your alpha ends up being over here, and there is some critical value right here. And then the last case, imagine you're going on a blind date and the person you're going with said that they're 5'8". So you're expecting somebody who's 5'8". What happens if they're 5'9"? Acceptable? Acceptable. How about 5'7"? Acceptable? Sure, right? So if we are expecting here and you get something that is just a little bit off, it's still okay. A little bit more, somewhere between 5'6" and you're expecting 5'8", so somewhere between 5'6" and 5'10". Acceptable. But if you get somebody who's 3 feet tall or somebody who's 7 feet tall, yeah, that becomes a problem, which means that what we have is we have some area on this side where things we're expecting here, we're not getting it. So either they got too big, or things on this side which got too small, right? Which become a problem. Which means that there's some part of this significance level is on this side, and part of the significance level is on this side. And now if we look up the critical values, we get those two. This is called a left tail. This is called a right tail. And this is called a two tail. So, left tail, right tail, and a two tail test. Yeah. Double checking. Nope, I am still talking to myself. All right, so this is. So now what do we test? Well, let's look at the test statistics. If we are testing statements about proportions, we're going to be using this. Wow, right? We've seen this before. And when we're talking about means, we're going to be using either or, and again the conditions here are no sigma Oh my god, we saw those things before. Yes, we did. Yes, we did. Alright, so let's take a look at something. Most vegans are happy, right? Vegans and vegetarians live 7 long, miserable, baconless years longer than meat eaters. So, I suppose they should be happy. So, if we have a claim that most vegans are happy, and we, sample a random selection of vegans. Let's say we take 500 of them. Maybe differently. Out of 500 asked 65% said that they are happy. So here it is. Sample a random selection of vegans. Out of 500 asked, 65 said that they are happy. Yay! Right. Let's solve it. So first things first, we need to find our null hypothesis. And to do that, we need to find the claim and the opposite. Well, what's the claim? Most vegans are happy. So P is greater than 0.5. What's the opposite? P is smaller equal to 0.5. Between those two, this one becomes h sub 0 because it has an equal sign in it. So P equals to 0.5, and this becomes the alternative hypothesis h sub 1. P is greater than 0.5. Cool. So we have this. We probably need somewhere to test it, so we need a test statistic. Out of all three of those, right, this one refers to proportion, so we're going to use this one. So z equals p hat minus p divided by p cubed divided by n. Well, let's see. Do we have p hat? Well, we have our sample, so it's right here, 0.65. Do we have n? Yes, we asked 500. Do we have p and q? Well, nothing here says p and q, but we have p and q right here. If our p equals to 0.5, then our q equals to 0.5 as well. So our test statistics becomes 0.65 minus 0.5 divided by 0.5 times 0.5 divided by 500. Alright, so this is the start. So now what we do? Well, we should, we should have a rejection region. We have no alpha, so let's say we're going to test at 5%. Let's test at 5% significance. So alpha equals to 0.05. Alright, we're looking at things that are bigger, which means that the area we're interested in is here. And how big is this area? Well, this area is 0.05. Alright, how big is this number? What's our test statistic? Well, let's take a look. 0.65 minus 0.5 divided by square root of 0.5 times 0.5 divided by 500. I got 6.71. So if our test statistic So here's the next question. Where does this region start? Well, if we look up that, right? Because if you look up 95%, you're going to get this. Where's this on this? Well, this is somewhere on this side. And because this is somewhere on this side, this is falling into the rejection region, right? This is failed to reject. And this is reject. And because our test statistics falls into our rejection region, the conclusion is we're going to reject the null hypothesis. If we reject the null hypothesis, we're going to reject the opposite. Which means we're going to support the claim. And that's the end of the problem. Alright, this feels really messy. Let's do more problems. Claim the hypothesis, the test statistic, the picture, the test, the reject, the support. Let's do more problems. Where is... Hang on a second. Right. Let's do some more problems. I am going to post this drill set online as well, so you have access to it. For people that are not in my class and are listening, here's a list. Take a screenshot if you want. And I'm going to focus on the top 3, let's see. All right, and let's make up some stories. So all right, let's make a story. A sample of 54 students, right? A sample of 54 students, showed 38.9% of them getting a scholarships. A sample of 54 students showed 38.9% of them getting a scholarships. Add 5% significance. Test the dean's claim that more than 31.5% of students, that more than 31.5% of students get scholarships. Here it is. A sample of 54 students showed 38.9% of them getting a scholarship at 5% significance test. The deans claim that more than 31.5% of students get scholarships. So what's the claim? Well, claim says that more than 0.315% of the students get. The opposite is that P is smaller equal to 0.315, which means that this becomes our H sub 0 because it is equality. P equals to 0.315, and our alternative hypothesis P is greater than 0.315. Again, just like any of these drills, gray are questions and blue are answers, but we're not worried about the answers. We're going to do all of it here with me. So this is step 1. Now let's look at our test statistic. We're talking about proportion, so our test statistic is Z. Z is P hat minus P, right, divided by PQ divided by N square root. So in our case, P hat is 38.9. Our N is 54. So this equals to 0.389 minus, well, there's our P, 0.315 divided by P. How much is Q? Q equals to 1 minus P, so Q equals to 1 minus 0.315, so Q equals to 586. Divided by 54. So our test statistics ends up being 389 minus 0.315 divided by square root 0.315 times 0.685 divided by 54. So our test statistic ends up being 117. So that's our test statistic. All right, what next? Next, we need some rejection region. There's our beautiful graph. We're looking at a right tail test. So we're looking at some area over here. And this size of this area is alpha equal to 0.05, which means that our critical value, right, corresponding to 5%, is the alpha equal to 1.645. Why do I say 1.645? Because on the standard normal table, I'm looking at 95%, because z-scores refer to the area to the left of the z-score. So if you look up z-score of 1.645, you're going to get this area, and the size of this area is 95%. So this is this. So question is, which region is reach? This is rejection, and this is fail to reject, which I like to just fail to reject, and we have a 0 in the middle. Where is this number? Well, this number is somewhere here. Right? This number is 1 is somewhere between 0 and 1.6, which means we fail to reject h sub 0. Well, if you fail to reject this, means we cannot support this, which means we fail to support claim. Which means that at 5% significance, we cannot support the dean's claim that more than 31.5% of students get scholarships. And that's how you do it. So how do I get all those answers when we failed one, we support the other? Let's think about it this way. Your claim could end up being either h sub 0 or h sub 1, depending on where the equality ends up being. And we could either reject h sub 0 or fail to reject. Right, those are the four options. Your claim was h sub 0, your claim was h sub 1, and we either rejected h sub 0, rejected, or failed to reject h sub 0. If we reject the h sub 0 and the claim was h sub 0, then we have enough evidence to reject the claim. If we reject h sub 0 and the claim was h sub 1, which means it was the opposite of what we rejected, we have enough evidence to support the claim. On the other hand, if the claim was h sub 0 and failed to reject, well, we do not have enough evidence to reject the claim. And if we fail to reject h sub 0 and the claim was h sub 1, well, we do not have enough evidence to support. Then this is how you do it. You just kind of build yourself a mental picture. If the claim was h sub 0, then you either reject or fail to reject it. If the claim was h sub 1, then you either support it or you fail to support it. So in our case, if we fail to reject h sub 0, fail to reject this, right, and the claim was h sub 1, well, we fail to reject it, claim was h sub 1, we fail to support. Now here's the little piece which is kind of cool. Is this whole enough evidence. What does mean enough evidence? Well, it means that as our sample gets bigger and bigger and bigger, all claims which are not perfect match for the population are going to get rejected. So if you make a claim that is not matching the population, the true population parameter, right, the census population parameter, if you make a claim that is not matching it, even if it's a little bit off, there is a sample that is big enough to reject it. If you take a small sample, the claim and the actual population thing could be quite different. But as your sample size grows, the difference between what you assumed about the population, what we found out about the population, is very different. Right? The important part here is that what we have is we have some assumption of what the population is going to be like, right? That's our H sub 0. And then we're going to get a sample. And this sample is much more indicative of where the population thing is, right? Because we know that samples approximate, right, population. We did that. We took a sample and we did a confidence interval for population. So the population is hiding somewhere near the sample. And eventually, if these two things are far enough apart, we're going to reject the assumption, because this is the important part. This is where we are like, yeah, we got this, we can feel it, right? So if we go back to my little pen thing, right? And we say all the pens in here are black, right? By the way, there's, just so we are clear, there's two pens that are different colors. There's a red one and a green one. But if I say all the pens in this population are black, and I take a small sample, I'm most likely not going to pick one of the different colors. And we look at this and we're like, hey, I have no reason to doubt it, but I don't have enough evidence to support it. Right? We have, okay. Right? And then you take a bigger one, and eventually you're going to get a sample that is big enough, and you're like, whoa. You said all pens are black. This is off, right? If you said most pens are black, well, this is still kosher. But when you say all pens are black, no, they're not. There's a green one, right? So if we make the claim all pens are black, which is P equals to 1, right? Well, we have enough evidence to reject the claim. On the other hand, if you just took a small sample, we don't have enough evidence to reject the claim. Right? On the other hand, if you said, hey, most pens are black, we have enough evidence to support, right? Because the opposite of most pens are black, not, there is no black pens, less than 0.5%. So, right, so we can build this kind of a setup. And the whole question goes always to, hey, what is enough evidence? And again, the bigger your sample, the more secure you can be that this is getting closer and closer to population. If theirs is getting closer and closer to population, then how come they're mismatched, right? How come we have this space right here? And the bigger the sample, right? So as n grows, or n grows towards n, right? This distance is going to get more and more obvious, unless again the assumption, or right, the claim that we have, or the opposite of it, right? Unless this is matching the population very closely, as our sample grows, this whole thing just kind of spreads around, and eventually it's very obvious that those two things are different. So this is this kind of concept of is it enough. All right, let's do one more while we edit. So let's do number 2. Let's pick on students. So out of 150 randomly selected students, 76 passed their driving test. At 5% significance, test the claim that 59.3% of students pass the driving exam. All right, well, claim opposite. Now again, the drills you see up here, they're designed in such a way that you can pick and choose both which one is your claim and which one is the opposite. Best way to do it, just flip a coin. This will give you the most practice with this kind of setup. So that's one. Second one is there's always, or usually there's a lot more information than needed. For example, in this case, I both give you a number of successes and a sample proportion of success. So you have to kind of pick and choose which one do you want to use. You can use both. You can use just one of them. You don't have to use both at the same time. So we're gonna, this time around we just chose the number of successes, and we're gonna go with there. So claim was that 59.3%. So what's the opposite? Well, the opposite is not equal to. Right, percentage is decimal place. This becomes h sub 0, this becomes h sub 1. P equals to 0.593. P does not equal 0.593. Right, test statistic p hat minus p divided by pq divided by n. Let's see, we have p 0.593. We can get q 1 minus this, so 704. So we have q. We have n 150, and we have 76. That's not a p hat. That's an x. So we have an x at 76. X meaning the number of successes. So what's p hat? P hat equals to x divided by n. So in our case, 76 divided by 150. 76 divided by 150, which comes out to be 0.5067. Alright, so our test statistic becomes 0.5067 minus 0.593 divided by 0.593 times 0.407 divided by 150, and there's a square root here. So our z statistic, our test statistic is going 0.5067 minus 0.593 equals divided by square root of 0.593 times 0.407 divided by 150. And we get our test statistic at negative 2.15. And if you look at right here, negative 2.144. And the reason for it is I used one extra decimal place here. If you don't use this decimal place, you should get negative 2.1439, so 1.44. So there's a discrepancy based on how many decimal places I used. Alright, so we have our test statistic. So now the picture. Let's see, we're using 5% significance and we're using a two-tail test. So we have one little section here and one little section here. Two tails. So if our alpha equals to 5%, then alpha over 2 for this side is 2.5%. Alpha over 2 on this side is 2.5%. And if you look it up on the z table, you're going to get negative 1.96 and 1.96. And again, you get to see that right here in the critical values. Now, I tell you that there's two critical values in this column, and in this column I tell you only the critical value that is actually relevant to the test. Why is it relevant to the test? Well, because negative 2.13 is about here. Negative 2.15. It's right here. And again, if the middle is the fail to reject, this means we reject the null hypothesis. And if we reject the null hypothesis, we reject the claim. So bam. And that's how you do it. And again, you have a whole set of drills here for it. And well, the second thing I'm going to be posting, which we're going to do a problem of, is I'm gonna be posting a set of problems for means as well, because we can do that as well. So there's a whole list here. And again, you have your sample size, your standard deviation, you have a sample mean, you have a significance level, you have both hypotheses written out, you have a critical value, one or two tails, you have a test statistic, and then the test result. And let's do the top one just so we are. Again, screenshot if you want, and let's look at the top one. Let's make up a story. What kind of story we gonna make up for this one? Alright, let's do this way. The mayor claims that $193.5 a week is enough to feed a family of 4. A search of the archives provided a standard deviation of $66.4 a week and a sample of, I should say a random sample of 17 low income families showed average food expenses at $240.6 a week. Test mayors claim at 1% significance. Here it is. A mayor claims that $193.5 a week is enough to feed a family of 4. I should say a low-income family, but a search of the archive has provided a standard deviation of $66.4 a week, and a random sample of 17 low-income families showed an average food expenditure of $240.6 a week. Test mayors claim at 1% significance. Alright, well, let's do it. So what do we have? Well, let's say we have alpha at 0.01, so we don't forget that. We have some claim. And the claim is saying that mean equals to 193.5. The opposite of that is that mean does not equal to 193.5, which means that no hypothesis is mean equals to 193.5, and the alternative hypothesis mean does not equal to 1. Now, this might seem repetitive. I write 193.5 4 times, but it will prevent me from making mistakes. Alright, family of 4. Does this matter? No, so we are not worried about this, provided some standard deviation of 66.4. N equals to 17, and we have some x bar at 240.6. Our test statistic, again, we have sigma, so our test statistic is this one. So in our case, that's 240.6 minus, right here, 193.5 divided by 66.4 times square root of 17. And that makes our test statistic equal to 240.6 minus 193.5 divided by 66.4 times square root of 17. 292.5. And here's our test statistic. Alright, so what else? We need a picture. And what are we looking for? We're looking at 1%, and we're looking at two tail. Right, alpha is this. So if it's a two tail, there's two of those. And again, if you look up 0.05%, you're going to get 2.575 and negative 2.575. Failed to reject is in the middle, rejection region is on the outside. And where does our statistic end up? Well, our statistic 2.925 ends up over here somewhere. 2.925, which means what? Which means we reject h sub 0, and if we reject h sub 0, right, we reject the claim. And if you want to be really cool, you can write the claim out, but that's not necessary. And that's how we do it. And that's all there is to it. And that's chapter 5 in a nutshell. At least what I would expect most people to know. And by now, which is a month and a half before the final actually rolls in, you should be able to do about 90% of the final exam. If that's not cool, I don't know what is. Alright, so this covers chapter 5, and next week I'll probably run a bunch of drills. So I will take the problems that you guys see above, and I will just do a bunch of problems. So hopefully by then some of you might have questions on how to do anything else, and so next week we're going to be doing problems. All we're going to be doing is problems, and then week after that we're going to start on chapter 6, which is chi-square testing. And after that, some real of problems. After that, some chance for some of us to pick up some extra points and whatnot. And after that, it's all practice, practice, practice. So in about 4 weeks, we should be done with enough, and then it's just a question of getting it polished and better. So again, if you have any questions, just shoot me an email, post a comment, and I'll take it from there. Otherwise, I'll see you guys next week. Thank you for joining me.